Okay, so let's continue with the revision of our chapter capacitor. So let's begin with the question 1. So let me just zoom it for a bit. Okay, so for the question number 1, it's about the circuit below. Show an uncharged capacitor. So uncharged capacitor is actually a keyword for us. So it means that when the switch is closed, the capacitor is ready to be charged. So this is actually an uncharged capacitor of capacitance. Okay, so my C is basically 5 millifarad. So 5 millifarad is basically times 10 to the power negative 3 farad connected to a 6-volt battery. So my electromotive force basically is 6 volt of battery and a 12 kilo ohm resistor and a switch. So the switch is closed as at time t is equal to 0. So my resistor is actually 12 times 10 to the power of 3 ohm. Okay, so for the question A, sketch a graph to show the current supplied by a battery varies with time. So we know that this circuit is actually show us the charging CR circuits. So what we need to do and draw is to draw the graph of the charging CR circuits. So for the charging CR circuits, the current, so this is the current and this is the time. So the current inside the circuits will initially is actually I0. So after certain time, it will eventually decrease exponentially at certain time t, or I can say that the I will decrease until infinity, or I can say that until at certain time. So this will be the curve for the current. So at time t, the current basically is equal to 0 since the capacitor is fully charged. Okay, so let's move on to number 2. So the voltage across the capacitor varies with time. Okay, so for the CR charging circuits, we know that. Okay, so based on the previous video, we talked about the formula for the potential difference, the charge, and even the current. So the formula for the current basically is I is equal to I0 multiplied by e to the power of negative t over CR. So this is the current for the charging CR circuits. As for the potential difference for the charging CR circuits, so my V across the capacitor is actually equals to V0 bracket 1 minus e to the power of negative t over CR. So basically this is the formula. So what will be our graph? So my graph here will be, so this is initially is 0 of course, so this will be my V0. So this will be my curve, and I can say that the potential difference across the capacitor is basically increased at and fully charged at a certain time t. So when the capacitor is fully charged, the value for the potential difference across the capacitor is actually V0. So this is how the graph of the potential difference works. Okay, so as for the number 3, okay, so the voltage across the resistor varies with time. So this, if I'm not mistaken, we haven't discussed from the previous video. So this is across voltage across the resistor. Okay, so for the explanation, so this is our circuit. So when the switch is closed, 6 volt, this battery will eventually release current. So this current will eventually flows throughout the circuits. So initially, the current that obtained by the capacitor and the resistor is actually the same since the circuit is in the series form. So okay, so the potential difference across the resistor initially is maximum. So I can say that this is the VR. So initially I have the potential difference of VR. And finally, when the capacitor is fully charged, so there's no more current flowing inside the circuits, and hence the resistor finally, the potential difference across the resistor finally will become 0. So I can say that my VR is actually equals to V naught e to the power negative t over CR. Okay, so this will be my graph, and this is the potential difference, and this is the t and 0 and the okay, so and the graph will decrease exponentially throughout the time, along with the time. So this basically is the V naught. So let me check for a while. If I'm not mistaken, the graph should be correct. So let me check for a while. Okay. Yeah, this is the correct way to draw the potential difference of the resistor throughout the time. Okay, so let me find where is the okay, so let's continue with the question B. So this basically is the graph for the charging CR circuits. Okay, so let me erase all this one. Oops, I accidentally erased the information I wrote just now. So let me drag down for a bit. Okay. Oops. Alright, so come on, let me just drag it up. Alright, so basically this one is the resistor. So my resistor is 12 times 10 to the power of 3 ohm. Alright, so for the question B, calculate the time taken for the voltage across the capacitor to be equal to the voltage across the resistor. So the question asks about the time taken when the voltage across the capacitor is equals to the voltage across the resistor. So we know that the voltage that produced in the capacitor and the resistor is basically came from the power supply, which is the battery. So if we wish to find out the potential difference, which is for the both capacitor and the resistor, which are equals to each other, so hence we need to divide this potential difference of the battery into how should I describe this? So we need to divide this potential difference for the battery, not potential difference, should be the electromotive force by 2. So 6 over 2, what I get is actually 3. Okay, so I can say that when both of them are equal, so I have the 3 volts for the capacitor and 3 volts for the resistor. So hence my V is equal to V naught. So this is 1 minus E to the power of negative T over CR. Okay, so this is the formula that we need to apply in order to find out the time taken. Okay, so this is 3. So the maximum capacitor that can the maximum potential difference that can be obtained by the capacitor is actually 6, since the battery the electromotive force supply is actually 6 volt. So my maximum voltage is actually 6. So this is 1 minus E negative T. So this T is the one that we need to find. So the C, the capacitance, is actually 5 times 10 to the power negative 3. So the resistor is 12 times 10 to the power of 3. Okay, so what we need to do is just calculate it. Okay, 3 over 6. Alright, so 1 minus answer. Okay, so the ln answer times the negative 5 times 10 to the power negative 3, so 12 times 10 to the power of 3. So what I get for the final answer basically is 41.6, or I can say is actually 41.59. So at the time, which is 41.59, so the potential difference across the capacitor is equal to the potential difference across the resistor. So this is the way that we calculate for the potential difference. Alright, so we have done for question number 1. So let's move on to question number 2. Okay, so let me just drag it down. Come on. Alright, so question number 2. The circuit below shows a capacitor which is initially charged to 9 volts. So the capacitor is initially charged to 9 volts. It means that the maximum capacitance, the maximum potential difference across the capacitor is actually 9 volts. That is being discharged through a resistor when the switch is closed. So I can say that the circuit is actually showing the discharging CR circuits. So it takes 20 seconds to reduce the 9 volts to 4.5 volts. Sorry, this is the 4.5 volts. Okay, so what is the time constant of the circuits? Alright, so the time constant basically is the, okay, let me see for a while. So the time constant basically should be, okay, let me just observe for a while. Okay, I have my 200 kilovolts, so I have my 9 volts. Okay, so what I need to find basically is C. So I do not have my C here, so what will be my C? Alright, so So I just need to find out what is the C here. Okay, let me just observe for a while. The circuit below shows a capacitor which is initially charged, okay, being reduced. Alright, so I have the idea. So this is the discharging circuit. So what we need to use is the formula for the discharging circuit. So V is actually equals to V naught multiplied by e to the power of negative t CR. So if this one is actually 4.5 and this one is 9, so the time taken for the potential difference from 9 to reduce to 4.5 is actually 20 seconds. So this is the CR. So this CR is what we need. So CR finally is, okay, 4.5 divided by 9. So the ln answer, okay, negative 20 divided by the answer. So okay, let me observe for a while. So the final answer basically is 28.5 seconds. I'm sorry, not 28.5, should be 28.85. So this is the time constant for the capacitor, for not the capacitor, time constant for the CR discharging circuits. Okay, so how long will it takes for the voltage to reduce from 9 volts to 1 volt? So the question is actually asking about the time taken for the potential difference across the capacitor to reduce from 9 volt to 1 volt. So basically the formula is the same. So this time the volt is actually 1 volt and the maximum volt is actually 9. So this is E and T is the one that we need to find. So the CR from the question A is actually 28.85. So the T will be, so what will be our T here? Ln answer times the negative 28.85. So basically the answer will be 68.39 seconds. Is it correct? Okay, I think it is correct. Okay, so sorry, that is a mistake here. Okay, let me see what is the mistakes. Sorry, this one should be 63. This one should be 63.39 seconds. Okay, so yeah, this is the question number 2. Alright. So let's move on to question number 3. Okay, let me just drag it down for a bit. Alright, so I hope you can see that. Okay, so number 3. So 4 capacitors of the capacitance 100 microfarad, 200 microfarad, 300 microfarad, and finally 400 microfarads are connected to a battery between the 2 points X and Y as shown in the circuit below. Okay, so let me just check whether the value is arranged correctly. Yeah, the value is actually arranged in order. Okay, so Question A. If the 100 microfarad capacitor has the charge of, okay, so this is the charge for 1 microfarad capacitor, has the charge of 700 mil coulomb. So determine the quantity of charge stored in the 200 microfarad capacitor. So through a 200 microfarad capacitor, we can see that 100 microfarad and 200 microfarad capacitors, both of them are actually arranged in parallel. So not parallel, sorry. Both of them are actually arranged in series, and we know that the concept for the charge is actually same as the current, which is the Qt is actually equals to Q1 is actually equals to Q2. So I can conclude that my 200 microfarad, the charge for the 200 microfarad capacitor basically is 700 microcoulomb. So this is the number 1. So determine the quantity of charge. So let me just zoom it for a bit. So determine the quantity of charge stored in the 400 microfarad capacitor. So okay, let me just observe for a while. Okay, so based on the formula, Q is actually equals to CV. So the Q for the 400 microfarad is actually equals to the, okay, so how can I find out this one? Okay, let me just observe for a while. 400 microfarads. Okay, so basically we actually need to find out the effective capacitance in this parallel circuits. Okay, so the effective capacitance, as for the parallel capacitance, we know that Ct is actually equals to C1 plus C2. So 300s plus the 400s is actually 700 microfarads. So my Ct is actually 700 microfarads. So okay, so the Q is actually equals to CV. So the charge, okay, so this charge is the total charge equals to the total capacitance multiplied by the voltage. So we are going to find out what is the potential difference in this parallel circuits. So my Q is actually 700 microfarad, not microfarad, sorry, should be times 10 to the power negative 6 equals to the total capacitance 700 microfarad as well. Okay, so microcoulomb V. So my V basically is 1.00 volts. So I got the answer for the potential difference of 1 volt. So basically the question is actually asking for the charge. Okay, so Q is actually equals to CV. So my Q for the 400 microfarad, so C is the 4 microfarad, sorry, so this one is basically is 400 times 10 to the power negative 6 times 1. So is it correct? So let me check for a while. Okay, so I think yeah, the question the charge is actually 400 microcoulomb. Sorry, microcoulomb. Yeah, this is how we calculate for the charge which exerted on the 400 microfarad capacitor. So for the first steps, we need to find out the total capacitance which the capacitor which are arranged in parallel. So the total capacitance found, we can finally find out what is the potential difference across these two capacitors. So in parallel, both of them, the potential difference for the two capacitor is actually the same, since both of them are arranged in parallel. So both of them has the 1 volt of the potential difference. Okay, so after obtaining this 1 volt potential difference, so we can find out the charge exerted by the each capacitors respectively. So the question in this case, the question asks about the 400 microfarads. So what we need to do is actually find out the charge for the 400 microfarad capacitor by using Q is equal to CV. So C is the capacitance of the 400 microfarad capacitor multiplied by 1 volt. So finally, the charge exerted by the 400 microfarad capacitor is actually 400 microcoulomb. So this is the way that we calculate. Alright, so calculate the potential difference across the X and Y. Okay, let me just erase all this one. Okay, let me just drag it down, drag it up for a bit. Okay, so alright, so let's move on to the question B. So calculate the potential difference across the X and Y. So we know that from the previous part, we already calculate the potential difference in this parallel circuit. So this is actually 1 volt. So we have 1 volt here. So what we need to find is actually the potential difference across the 100 microfarad capacitor and 200 microfarad capacitor. So let's calculate one by one. So Q is equals to CV. So my Q across the 100 microfarad capacitor is actually 700. 700 microcoulomb is equal to 100 microfarad multiplied by V. So V is the one that we need to find. So cancel, what I get is actually 7.00 volts. So as for the 200 microfarad capacitor, so this is 700 as well. So the capacitance of the capacitor basically is 200 microfarad times V. So cancel. So what I get finally basically is 3.50 volts. So the question asks about the potential difference from A to B. So what we need to do is actually find out VAB, which is the sum of these three potential difference. So I have the 7 volt plus the 1 volt plus the 3.5 volt. So adding up all the three potential difference, so what I get is actually 11.5 volt. So is it correct? So let me check it. Yeah, the answer is correct. Alright, so this is the question number 3. So let's move on to question number 4. Okay, so let me just erase this one. Alright, so let me just drag it down, come on. Okay, so for number 4, a parallel plate capacitor of the surface area, so my surface area basically is 0.24 meters square, has a plate separation of the 0.65, so centimeter is times 10 to the power negative 2 meters. In free space, so free space basically meant by the permittivity of free space, which is epsilon naught. Okay, so and the potential difference of 0.80 kilovolts. Determine the charge stored in the capacitor. So the charge stored in the capacitor. Okay, so what we need to do is find out the apply this formula, of course. Q is equal to CV. So the problem is we did not have the capacitance, so we need to find out the capacitor the capacitance of the capacitor using this information given. So C is equals to epsilon naught A over D. So the permittivity of free space basically is equal to, so let me just check for a while. So this basically is 8.85 times 10 to the power of negative 12. So my surface area 0.24. So divided by the plate separation 0.65 times 10 to the power negative 2. So what we have here is okay, 0.65 times 10 to the power negative 2. So what we have is actually 3.268 times 10 to the power of negative 10 farad. So this is the capacitance of the capacitor. So finally we can substitute this formula. So let me check for a while. So the question is actually asking about the charge. So 3.268 times 10 to the power negative 10 times the potential difference, which is 0.8 times 10 to the power of 3. So basically the final answer is 3.268 times 10 to the power negative 10. So 0.8 times 10 to the power of 3. So the final answer for the charge is 2.614 times 10 to the power negative 7 coulomb. So this is the final answer. So let me check for a while whether it's correct or not. Yeah, the question is correct. And the answer is correct. 2.614 times 10 to the power negative 7. Alright, so let's move on to the question B. Okay, let me just erase all this one. Okay, so I just write it down here. Column. Okay, let me just erase all this one. Alright, so let's move on to the next question. So is it question B? Okay. Alright, so let me just drag. Okay, so question B. So this is the information from the previous question. So is it related? So I think, okay, never mind. So the charge capacitor is then discharged through a circuit connected to a resistor of 10 volts, resistor of 10 kilovolts, kilo ohm, sorry. Determine the time taken for the charge in the capacitor to decrease to half of its initial value. So half of its initial value. So the time taken for the charge, okay, to decrease to its half initial value. So the C just now, what is the capacitance for the capacitor? So epsilon naught 8.85 times 10 to the power negative 12, 0.65, because I need the capacitance for the capacitor to answer the next question. So the capacitance for the capacitor is, okay, so 3.267 times 10 to the power of negative 10. Okay, so this is farad. Okay, so the charge. So since this is the discharging circuits, so what I have here is the formula for discharging circuits. Q naught e to the power negative t CR. Okay, so the question asks about the time taken. So this is the t that we need to find. So the charge is reduced to half of its initial. It means that this is actually Q naught over 2. So this is Q naught. So this is the T over CR. So this can be cancelled, and 1 over 2 is equals to the E negative T over CR. So the C is the 3.267 times 10 to the power negative 10. So the R is 10 times 10 to the power of 3. So the time taken, so what will be the time taken? So ln 1 over 2 times the negative 3.267 times 10 to the power negative 10 times the 10 times 10 to the power of 3. So the time taken for the capacitor to the charge of the capacitor to reduce to its half of its initial charge is actually 2.265 times 10 to the power of negative 8 seconds. So let me just check whether it's correct. So let me check the answer. Okay. So this is the question B1. So 2.265 times 10 to the power of negative 6. Okay, correct. Okay, so this is the question number 1. So what about the question number 2? So the current, determine the current after 2 microseconds. So my current, my time is 2 microseconds. So for the discharging circuit, it's actually same as the charging circuits. The formula for the current is basically the same, which is the same as the charging CR circuits, which is I is equals to I naught multiplied by E to the power of negative T over CR. So okay, let me just find out what is happening here. Alright, so the current after the time 2 mu s. Okay, let me just find out. Alright, so I think that it is not necessary to write this, to apply this formula. So if I'm not mistaken, I actually can use this formula directly, which is Q is equals to IT. So my charge is okay, so I can find out what is my charge. No, sorry. This is not working actually. Okay, so let me just find out what is the, so what will be my solution for this question. So let me think for a moment here. So okay, so let me just think for a while. So I did not have my Q naught here. Okay, so 2 milliseconds. So how should I calculate this one? Okay, so let me think for a moment here. Okay, the time taken for the charge to decrease to its. So I think the question 1 and question 2 is actually not related. So the charge is discharged. Okay, the question did not give any further information, just give the time taken after 2 microseconds. Okay, so I wonder what will be the way to calculate this one. I did not have my charge after the 2 microseconds, so I did not have my I naught as well, E negative T over CR. So I do not have my I naught, so this is not applicable actually. So what will be the solution? Okay, let me just think for a moment. Okay, so what will be the solution? Okay, so alright, so okay, so this question is actually quite confusing. Okay, I need to think for a while. Alright, so okay, so I think we just skip for this question. So I think we'll skip for this question for a moment, or I shall record another video for this question specifically. So we just skip this question first. So let's move on to the question number 5. So the question 5, define the capacitance of the capacitor. So we know that Q is actually equals to CV. So the C is actually equals to Q over V. So this is the definition for the capacitance, which is defined as the ratio of the electrical charges to the potential difference across the plate. So this is the definition for the capacitance of the capacitor. So for the question B, derive the expression for the effective capacitance of the two capacitors which is connected in series. So series, we know that in series we have the potential difference. The potential difference in the arranged in series is actually equals to V1 plus V2. So Q, this is the Q over C1 plus Q over C2. So this is the Q over CT as well. So Q can be cancelled. So finally what I get is actually 1 over CT is equals to 1 over C1 plus 1 over C2. This is the derivation for the effective capacitance for the capacitor which connected in series. Alright, so let's move on to the question C. Okay, let me just erase all this one. So the question C. So let me just drag it down for a bit. Okay, come on. Okay, so question C. Capacitance C1 and C2 are connected in series with a battery is shown in the diagram below. So determine the charge stored in each capacitor. So the charge stored in the capacitor basically is Q is equals to CV. So in this case, my electrical charges is actually the same for the both C1 and C2 since both of them are arranged in series. So what I need to do is actually find out the total capacitance. 1 over CT is equals to 1 over C1 plus 1 over C2. So the 1 over CT is equal 1 over 2400 plus 1200. So my CT basically is 1 over 2400 plus 1 over 1200. So my total capacitance basically is 800 microfarad. So Q is actually equals to the CTV T as well. So this is the 800 times 10 to the power negative 6 times the total potential difference exerted by C1 and C2, which is 6. So the charge finally what I get is actually negative 6 times 6. So the charge will be 4.80 times 10 to the power negative 3. This is column. So is it correct? So let me just check for a while. Okay, so this is the answer. Alright, so this is C1. So what about C2? Determine the total energy stored in the capacitor. So the total energy stored in the capacitors, which is U is equals to the half Cv square. So the total capacitance is 800 times 10 to the power negative 6. So the V is 6.0 square. So what I have here is actually 1 over 2 800 times 10 to the power negative 6 square. So basically I got my answer, which is 1.44 times 10 to the power of negative 2 joule. Okay, so this is the question number 2. So question number 3, calculate the energy supplied by the battery. So the energy supplied by the battery is actually equals to the work done is actually equals to the QV. So my Q basically is 4.8 times 10 to the power negative 3. So this is 6. So 4.8 times 10 to the power negative 3, and this is 6. So what I get is actually 2.88 times 10 to the power negative 2 joule. So this is the answer for question number 3. So what will be the question number 4? So comment on your answer in C1 and C2. So there is actually a difference between C1 and C2. Not C1 and C2, sorry. C should be C2 and C3. So there's an error here. So C2 and C3, basically the answer between them is actually the difference is actually 2 times. So 2.88 is actually the 2 times of 1.44. So I can say that the half of the energy when the electrical energy is supplied to charge the capacitor, half of the energy is dissipated as heat to the surroundings. So I can conclude that half of the energy is dissipated as heat and lost to the surroundings. So yeah, this is the explanation. Half of the energy is actually dissipated as heat and lost to the surroundings. Or I can say that half of the energy is used to overcome the resistance which exerted by the wire. So this green line is actually the wire. So that's another explanation, but the best explanation is actually half of the energy is dissipated as heat and lost to the surroundings. So this is question number 4. So number 5, the final questions. So the capacitor C1 is actually removed and allowed to discharge through a resistor of So my C1 is, what will be my C1 here? So C1 is 2400 microfarad. So the resistor given is 250 ohm. So determine the time taken for the charge to decrease to 60%. Okay, so decrease by 60%. It means that, okay, so this is actually the discharging circuits. Okay, so basically this is my formula, of course. So decrease by 60%. Okay, so this is the 0.660 of initial charge. So this is the T that we need to find, 2400 times 10 to the power negative 6. So this is 250. So my T will be, so my T 0.6 ln 0.6 times the negative 2400 times 10 to the power negative 6, so 250. So the time taken is actually 0.306 seconds. So is it correct? Okay, so actually that is a mistaken here. So the decrease by 60%, it means that the charge left inside the capacitor is actually 0.4. So this is actually a careless mistake. So the charge left inside the capacitor is 0.4. This is because the charge is already decreased by 60%. So let me just calculate again. 0.4 times negative 2400 times 10 to the power negative 6, 250. So the final answer, 0.549. This is the time taken. Alright, so this is how we calculate and the technique answering the question of the chapter capacitor. So the I think for the most confusing part is basically the charging and discharging circuits, and the other else is actually still okay. And if we understand the concept, we are able to do it step by step according to the formula that we learned. Alright, so that's it for the question, all the 5 questions. So I left one question, which is the question 4b and part 2. So I'll do for another video for this question. Okay, so I'll think for a moment because this question is quite confusing for me. So I'll record another video for specifically for this question. So I think we'll stop here now. So if there is any question need to be asked, please comment below this video. So I'll see you next time. Thank you. Bye.